Okay, so hi everyone. I'm going to present our work on robot learning of mobile manipulation with reachability behavior bias. This is a work we're doing at the IROSA lab at TU Darmstadt. So when I talk about mobile manipulation tasks, we're typically talking about these kind of pick and place kind of tasks with a mobile manipulator that has a base and an arm. And typically to actually perform these tasks, not only must the mobile manipulator be able to perform the task with its arm, but it also needs to first, as a precursor to the arm manipulation, decide on a good base position to subsequently attempt the actual manipulation. This is something that we humans can do quite intuitively. We have an intuitive idea of the reach of our embodiment, and we have an intuitive idea of the geometry of the scene. So which objects can block me, which obstacles can block me, and where should I place myself? So we propose using learning and reinforcement learning for this problem of learning optimal base placement, because we can adapt to the geometry of the scene quite well with the learning method. And in this work, we're going to study the integration of robotic reachability priors in RL methods for accelerating this learning. So the method we propose is called boosted hybrid RL. And what it involves is first learning simpler reachability tasks, and then using the learned behavior as a prior for accelerating the learning of subsequent tasks. A reachability task could look like something like this. You have a 6D goal that the robot needs to reach, and then it needs to place itself at the correct position and orientation so that it can actually perform that reaching task. So you can teach a robot to reach this particular 6D pose. And what you see at the bottom here is the learned Q function of the robot that it learns. So given a target 6D goal, which is the purple arrow here at the bottom, it learns what is a good base pose to put itself. The dark blue here signifies a maximum likelihood of reaching. What we're going to do on top of that is we're going to model the Q function. We're going to learn multiple tasks, and we're going to model the Q function as a sum of residuals learned on each task. So we learn a residual network instead of a Q network for each task, and the sum of these residuals becomes our Q function. We also add some regularization on the previous policy in a trust region fashion to not deviate too far. And in mobile manipulation, we propose using this hybrid action space model because typically you need good coordination between the arm and the base, and this could require the combination of both discrete and continuous actions. So what does this look like? How the learned tasks look like? So on the left is what we already saw, some simple reaching tasks for a 6D goal in free space. On the bottom, we increase the distance threshold for where the goals are, and you learn a residual that can handle distances. You can then progress further to obstacles, different obstacles with a goal in the air, or different obstacles with a goal on a particular table. You can also progress further with some kind of settings you might have in the lab, which is, let's say, a wall blocking your path, and the most interesting one, which is multiple objects on the same table. On the bottom right, you see the agent with multiple objects, and what you can gather is that because the agent could accidentally collide with one of the other objects, it tries to give the other objects a wide berth while it tries to navigate towards the object that it is the target object that it needs to go to, just so that it doesn't reduces the likelihood of colliding with any of the other objects on the table. So the learned policy from those final agents we transfer to the real system. And over here, we have the video of behavior on the real system. Again, on the right is the Q function of the agent visualized. Dark blue, again, of the Q function signifies points that are high likelihood of reaching. Of course, for this demonstration on the real system, we do assume that we know the object and the obstacle positions beforehand. So the bounding boxes of the obstacle, the table, and all the objects are known. And the agent is reasoning about the geometry of the scene and accordingly deciding where to place itself. And that can be seen from the Q function over here. I'm going to speed this up a bit to to see the next task, which is a slight modification of this task, which is a rearrangement task. Because you can do picking, of course, you can now also do pick and place. So in this one, the robot has to pick a particular object on a table and then place it on another target location on another table. And again, similar principle, it goes and performs the task again by choosing a good base placement. Yeah. So yeah, the robot can perform reasonably well for these kind of tasks. Typical failure cases on the real system we noted were situations where the learned policy outputs a goal that is a bit too close to the table and no safe plan was found by the real system. Some differences between the simulated base placement and the real base placement, where in simulation, the agent is braver and wants to go closer to the table, while the real system doesn't want to go as close to a table as possible. But we did find pretty good performance on the real system as well. And with that, I'd like to finish and open up to questions.
Thanks so much, Sneha, for the great talk. Does anyone have any questions? Yes, there's one question.
Hi, thanks for the presentation. I was wondering, will you consider also oriented base towards looking where the objects are instead of like blindly picking?
Yes. So the base placement also considers orientation. Of course, what I've shown here is a 2D representation of the Q function, but the Q function also considers orientation. We let the robot choose what orientation is good, because especially for this robot, as you see, it has a significant reach on the sides of the robot. So many times the robot would prefer to reach from the side rather than look towards the object at the end. So we don't include some kind of orientation objective to the robot, but we let it choose an orientation that will likely succeed.
Thanks.
Are there any other questions? All right, thanks so much, Tim.
Thank you.
Next, we have Ying-Long Song. If you're there, please feel free to start sharing your screen.
Yeah. Do you see my screen?
And we can hear you too.
Okay, great. So, all right. So my name is Yun Long, and today I want to talk about my work on policy search for motor control with application to agile drone flight. So reinforcement learning is a very powerful method that can optimize black box policies, and MPC is a method that uses optimization and dynamics for the task of control. So both can be applied for robot control. One of the fundamental questions is how can we combine the advantage of both approaches? The most related work to my method is this one called policy search for motor primitives in robotics, in which you can basically encode the skill of the robot using parameterized motor primitives, and then learn these motor skills using policy search that kind of optimize the parameters for the motor primitives. And the main idea of my approach is that we can take MPC as a parameterized controller. So here's a general formulation of MPC, which minimizes some cost function. And essentially, the skill of the robot is encoded in this cost function. And basically, we can model these skills using this cost function and with some unknown parameters. By learning different parameters, the robot can achieve different tasks. To learn these unknown parameters, we first model these unknown parameters as a probabilistic policy search method, for example, using Gaussian policy. And then we can formulate the search of unknown parameters as a probabilistic policy search. And this problem can be solved very efficiently using weighted maximum likelihood, which has a closed form solution for the parameters of the policy. By combining different representation of the policy, we can learn different policies. For example, we can learn Gaussian policy for state independent parameters. And then we can learn linear policy for state-dependent parameters. We can also learn neural network policies for high-dimensional state-dependent parameters. And then we apply this approach, this framework, to one of the very challenging tasks in Agile flight, which is to fly through a dynamic gate. So the problem is that you have a quadrotor and you have a pendulum gate, and you want to fly from one point through the center of the gate and reach a goal position. And we can formulate this problem into an MPC formulation, and in which here, the unknown parameters that we mentioned before is the time to fly through this gate. So since we don't know this time, we can learn this time using the policy search method. So here's the learning procedure looks like. So initially, we have no idea when should we fly through the gate. So we just randomly sample some variables from a fixed range. And we have a Gaussian that has very large variance. After 2 iterations of training, we have a kind of learn a distribution of these time variables, and it's very likely between 0 and 2 seconds. And after 10 iterations of learning, we can learn this parameters time as kind of equal to 1.5 seconds. And here, by combining a neural network policy, which predict the time for the MPC, and MPC plan a trajectory, which is represented as red dot in this case. And this is planned trajectory that can pass through the center of the gate. And finally, we can deploy this system in the real world, in which we can draw a quadrotor that passes through the center of the gate. And here's another example of this real-world deployment. Yeah, so as a conclusion, we propose a framework that combines policy search and MPC. And the key idea is to take MPC as a parameterized controller. And we apply this to one of the challenge tasks, which is to fly through a dynamic gate. If you're interested, the code is open source and you can have a check it out. Now I'm happy to take questions.
Thank you, Yunlong. Are there any questions from the audience? Okay, we have a question.
So thanks for your talk. And my question was, how fast were your drones?
Sorry, I cannot hear anything. I can hear something, but not much.
Of the drone in the experiments? What was the speed of the drone in the experiments?
What is the speed of the drone? I think it's up to 3 or 4 meters per second.
Thank you.
But the pendulum is swimming quite very fast. So that's the main challenge, because it's moving very fast.
Yeah. So what was the speed of the pendulum?
I think it's also like 4 meters or 5 meters, even the linear speed.
Mm-hmm.
In that case, thank you, Yunlong.
Thank you.
All right, next we have Nicholas. If you're there, please start sharing your screen.
Hi, can you see my screen and can you hear me?
Yes, we can see and hear you.
Okay, perfect. Then okay. Yeah, so hello everyone. Yeah, my name is Niklas and I'm going to present you our work on graph-based reinforcement learning meets mixed integer programs and application to 3D robot assembly discovery. In this slide, we show a typical 3D robot assembly discovery scene in which the goal is to assemble this arbitrary 3D target shape given the available Tetris-like building blocks. Contrary to other assembly problems with known instructions, in robot assembly discovery, the agent neither has any information about which blocks to use and in which pose to place them, nor about the sequence of the execution. Related work that deal with similar scenarios propose end-to-end learning approaches, which however require extensive training, especially due to the huge combinatorial action space, and they are also typically hard to interpret. Alternatively, one could try to use approaches based on task and motion planning. However, they typically require a full analytical problem description and most of the time only focus on the motion generation part and assume that you already know the sequence of execution. Contrarily, in our work, we propose a novel hierarchical approach, combining the best of basically model-based optimization and model-free reinforcement learning for robotic execution and task sequencing. For this, on the high level, we solve a mixed integer linear optimization problem to basically try to find out how do we have to combine the building blocks to optimally recreate the desired target shape. However, on this level, we don't model the robotic execution as well as the task sequencing. This complexity is solved by the intermediate level, on which we are dealing with a graph-based reinforcement learning agent that heavily benefits from the prior knowledge of the higher level. To put the desired commands into practice, we use a grasp and motion planner on the lower level. In the next slide, I quickly want to explain you the intermediate level, which takes the prior, so basically the result of the mixed integer optimization, into account and is also informed by the lowest level that deals with the task of grasp and motion planning. So basically, how does this graph-based reinforcement learning for action selection work? So given the input scene, which you can also think of like as a scene graph, given the input scene, we basically create this graph of the environment in which the white nodes basically correspond to the primitive elements of the building blocks that are available. The green nodes correspond to basically voxels in the free space that we don't want to occupy. And the pink nodes correspond to voxels that you want to fill because they belong to the target shape that you want to recreate. And all of these nodes basically are described by their 3D position and by their type. Then next follow basically 3 rounds of message passing using state-of-the-art graph attention mechanism, which then gives us basically an encoded version of the graph. And as the assembly actions are defined relative between nodes, because we basically want to move building blocks to currently unoccupied voxels, we use the features of this encoded graph to predict the Q values for all the actions that are available. And then basically finally, we choose the actions with the highest values, but to take the prior into account, we only choose the actions that have been basically proposed by this mixed integer optimization that we ran beforehand. Now, to evaluate the methods, we did 2 main experiments. In this first experiment, we compared the performance of our method against 2 baselines, which are basically end-to-end learning methods, to evaluate the effectiveness of this high-level classical optimization. As you can see in this results table, the matrix shows that our approach performs substantially better. In the second experiment, we compare the method against using a heuristic for the intermediate level of action selection. So we basically compare one implementation of our method in which you use a heuristic method to decide on the action sequencing against using our proposed approach. And again, you can see that our proposed approach performs substantially better. And thus we conclude that basically the proposed structure and the hierarchy is indeed very effective to solve this challenging problem of robot assembly discovery. And in particular, the classical mixed integer optimization is a very effective prior to guide the exploration of the graph-based reinforcement learning policy, despite the huge combinatorial action space. And finally, we showcase the performance of the overall approach in the real world. thanks a lot for your attention, and yeah, I'm happy to take any questions.
Thank you, Nicholas. There is a question from the audience.
So just a clarification, in this work, do you assume you have access to the 3D poses of the blocks? You do?
Yeah, exactly. So for deploying it in the real world at the moment, yes, we assume that we have like perfect knowledge of the real world. So we assume, yeah, that we know the position of all of the blocks. And yeah, I think it would definitely be interesting to investigate like how we can incorporate this method better, basically, with also having like a vision-based post estimation pipeline.
My follow-up question is, if you have access to all the poses, why don't you just do task and motion planning? Why do you need RN for this? Because you assume you have access to the model.
Yeah, I mean, like the big challenge in this problem is that you not only have to find out basically the motion of how you put like the blocks from the one position to the other, but you really have this additional complexity of having to figure out like which blocks do you actually want to use and which of them you don't want to use. And if you would take this additional complexity into basically task and motion planning approaches, the solvers would be like way more complex, and it would, like, we think it would be very difficult to really solve all of this complexity. Yeah.
I see. Okay.
Any more questions? All right, then thank you, Nicholas. Next up is Shivansh Behaviour.
Can I start? Is my screen visible and am I audible?
Shivansh, we can barely hear you. Can you talk a bit louder, perhaps?
Just a second. Hello? Is my voice better now?
Could you talk a bit louder?
Hello? Is it better now?
Yeah, this is slightly better.
Okay. Anyways, like, I'll be sharing a video that I recorded for the presentation, so I don't think my voice should be okay. Good afternoon, everyone. I'm Shivansh Behaviour. I'm a master's student at IIIT Allahabad. I'm glad to present our paper titled Planning with RL and Episodic Memory Behavior Priors. The work is co-authored by Dr. Andrew Nalek. In our paper, we present a planning-based RL approach, which utilizes episodic memory to solve visually complex environments with high sample efficiency. Our method achieves near-perfect performance under 60 minutes of training, while concurrent methods require over 3 to 4 times more training time and environment interaction. We demonstrate our findings and result on Learn to Race environment, in which an agent is tasked to complete a Formula One style racetrack with minimum off-road driving violations in least amount of time. The environment provides first-person RGB views and velocity information while allowing steering and acceleration to be controlled by the agent. In order to search and plan efficiently, we encode the semantics of visual scenery using a combination of variation autoencoder and unit to produce embeddings of important objects in the scene. The intent for using semantics and not the RGB images, as is the usual case, is that it enables a comparison between similar states using Euclidean distance and interpolation between learned state values of semantically similar states, leading to better sample efficiency. We train our agent in a phase-wise manner, starting from bootstrapping the agent, which is akin to pre-training and imitation learning. To bootstrap the agent, we inject behavior priors. In Learn to Race environment, we design this to be a knowledge base of safe and unsafe states. To build this knowledge base, the agent writes straight, and upon termination of an episode, labels the last k frames as unsafe, while labeling others as safe. At the query time, the agent uses nearest neighbor search to determine if the state is safe or not. With this knowledge, the agent starts phase 2 of training. In this phase, if the agent encounters an unsafe state, it takes a random steering action. While not in an unsafe state, the agent writes straight. On the termination of episode during phase 2, we store the entire episode in our episodic memory for planning in RL phase. The goal here is to provide an initial set of trajectories for the planner as the agent starts the RL phase training. Some of these random turns would yield good transitions which the planner will pick up in the next phase. Here is an overview of the training scheme and the role of episodic memory in our approach. The planner controls the agent in the RL phase. It searches for any given input state, the best performant and similar experience in the episodic memory. Here you can see the planner compares 10 different stored trajectories based on the future value estimates V. The planner compares where the trajectory leads to in the near future. You can see how this trajectory actually unfolded in the past experience. Here you can see the cumulative value estimate of near future state is the highest for the first candidate trajectory. The planner then selects the action for the first candidate trajectory to copy in the query state, since it leads to the highest reward in the future, retrospectively. All the episodes in the RL phase are also stored in the episodic memory as the training progresses. To train an agent, the planner chooses between exploration and exploitation based on how well the latent neighborhood of a query state is explored. If the neighborhood is well explored and contains good to follow trajectories, the planner prefers exploitation. Otherwise, it prefers exploration. Additionally, it gives more weightage to the actions which are least explored while selecting an action during exploration phase. Here is a comparison between baselines on unseen track for the learn to race environment and a training step versus success rate graph. Our algorithm achieves 93% success rate on unseen track in under 60 minutes of training. In comparison, soft actor critic requires 40 hours of training on the same compute hardware and still struggles to perform on an unseen track. To conclude, with this paper, we highlighted the benefits of using search-based strategies to enhance sample efficiency and how appropriate state representations and behavior priors can help in few short learning of complex environments. Thanks everyone and have a nice day. Thank you. I'm open for questions. Is there any?
Thank you, Shivansh. Are there any questions from the audience?
Sorry, I cannot hear you. Okay.
Can you hear me now?
Hello.
Yep, Shivansh, can you hear me?
Yeah, I can hear you now.
I actually had a question. What was the reward function used to train SAT?
For soft actor critic, the reward function is same as so basically the reward function here is how much the agent progresses in a particular time step. So if you take one time step of interaction, how much percentage of the track you complete. So if you have a higher velocity, you complete a higher percentage in a one time step, and thus you get higher reward. At the same time, if you move out of the track, you will get a penalty which is proportional to your velocity with which you moved out of the track. So that's the reward function used to train all the other.
Okay,
So
so
it is like,
it was actually a dense reward.
yeah. So for the step, for the reward function.
That's interesting. Yeah. Any questions from the audience? No, thanks once again, Shivansh.
Thank you.
And last but not least, we have a presenter in person.
Web, are you looking for the slides?
Yeah, I had to relaunch from Yay Technology. Just one moment.
Hi everyone, I'm Roberto Giammarino from Istituto Italiano di Tecnologia, and today I'm going to present a design concept of a preparation framework for impedance-based behavior priors in reinforcement learning for enhancing contact-rich tasks. First, I'm going to give a bit of background about Cartesian variable impedance control. That is a very important concept in this talk. So usually when humans perform contact-rich tasks like manipulation tasks, they adapt the compliance of their arm depending on the requirement of the task. And this, from a robotic control point of view, can be translated into Cartesian variable impedance control, where the error between the dynamics of the error between the desired pose and the current pose of the robot is modeled as a mass spring damper system, as you can see in this equation. Now I'll give the motivation of the work. So first important point comes from this paper that was also cited this morning by Animesh Garg, where they proposed to use as a formulation of the action space the desired pose at the end effector plus the Cartesian impedance at the end effector of a robot that is controlled through a Cartesian variable impedance control. They showed that by using this action space formulation, they can bring some advantages like low sample efficiency, low energy consumption, higher safety, better sim-to-real transfer, and better robot transfer in simulation. So this is has a very high potential as a formulation of the action space for reinforcement learning. On the other hand, at the same time, let's say, a very promising paradigm for learning contact-rich tasks is reinforcement learning with guided exploration. In particular, we can collect some demonstrations from an expert, as is shown in the square that is highlighted in light blue. And there we can obtain a dataset, and this dataset can be used inside frameworks of reinforcement learning with guided exploration to guide the exploration. So to have some behavior priors that are nothing but distributions over actions that are conditioned on states. So in a certain state, we know better which are the possible actions that we have to take, and this thanks to our prior experience. Now our goal is to merge the 2 points that I've shown in the previous 2 slides. So the reinforcement learning with guided exploration, and in particular behavior priors, together with an impedance-based action-based formulation in reinforcement learning. In order to do that, we want to design a suitable data collection system. So in the next slides, I will first show the state of the art, so the literature review that we did, from which we gained some insights to develop some guidelines for a design concept, and then I show also a design concept. So first, let's start with the state of the art. First literature review that we did was about data collection systems. And in particular, we noticed that there are 2 ways that we can distinguish to collect data. The first is through machine-generated demonstrations, like the scripted policies, or we can train an RL agent and then use it as an expert. But it's harder to guarantee semantically meaningful and natural skills behaviors. And what I mean by that is that usually we want to have human-like behaviors as behavior priors, and this is of course easier to obtain when we generate demonstrations through humans. And here there are 3 works that were very insightful, from which we gained some insights to then propose our design concept. And then we did also a literature review about reinforcement learning with guided exploration, where we can see that there are some works on the bottom that need to have demonstrations that are task specific, while others that can accept task agnostic demonstrations. And we claim that the highlighted works are the ones that can work with task agnostic demonstrations are more promising, because they can use a larger set of data, and this has been shown effective in other machine learning fields. And also, we think that this is more similar to how humans actually learn, because humans have previous experience that is not related to the downstream task that we want to learn, and then they are able to learn a new task in a few trials thanks to these models that they have built of the world. So there's a bit of delay with this. Okay, so these are the guidelines that we developed from the literature review. The first is we need the data collection system to be simple. So we don't want to have lengthy procedures like calibrations, because these would prevent from collecting large amounts of data. And then should be also accessible, because we want to give the possibility to as many researchers as possible to use this framework to conduct research in this direction. Then it's very important that it is compatible with the reinforcement learning training framework. So not only from state and action space point of view, but also, for example, when we learn visuomotor policies, we want to avoid visual artifacts, and we want also the user and the robot, the user, I mean the expert, and the robot to share the same state and action. Otherwise, the causality between state and action might be compromised. And then we want also intuitiveness, because the human that demonstrates the behavior should be able to demonstrate a meaningful behavior. And at the same time, we can relax a bit the precision of the framework, because in reinforcement learning, we are able to improve our demonstrations. So we are able to outperform the expert, hopefully. And also, usually humans are able to correct system inaccuracies if provided with the right feedback. For example, with the visual feedback, they are able to correct positioning inaccuracies of the robot when teleoperating a robot. So this is basically the design concept that we proposed in this work. On the left of the slide, you can see that there is the design concept of an interface that we want to use to send the desired pose to the robot. So we have an Aruco marker that is tracked by a system of 5 cameras. Then we have 4 trigger buttons. The trigger buttons are used to command the impedances, the Cartesian impedances of the robot. In particular, we have 3 translational impedances and 1 rotational impedance. The 3 translational impedances are commanded along the three axes that you can see in the right figure. And the three axes are chosen in order to have the coupled impedance requirements for most of the benchmark manipulation tasks that we found in the literature. While for the rotational impedance, we will command the rotational impedance simultaneously along all the three axes. This reduces a bit the degrees of freedom that we have, but at the same time, we notice that for benchmark tasks, this is enough. And we have also, of course, a button for closing, opening the gripper. And finally, we have two cameras for building the state of the robot. One is a wrist-mounted camera, and another one is a static camera that is viewing the whole framework, the whole workspace of the robot. And these two cameras are the same views that the operator can see, and this is because we want to have, as I said before, compatibility of state and actions between user and robot. Then our future work is to implement the teleoperational framework that so far is only a design concept. We want also to test its usability with a multi-subject user study, and finally we want also to evaluate it in the context of impedance behavior drivers. Thank you for the attention, and I will answer to your questions.
Thank you so much. Are there any questions in the audience? I actually had a question. So one of the things that I notice with stuff like this is when you want to use a large data set, there's a lot of redundant data in it as well. I was interested to know why that wasn't one of the guidelines, or what was the decision to not have something like that? Yeah, what are your thoughts on that?
Yeah. So actually, when I received the reviews for this paper, I received a similar review, and this was not inside the guidelines because the guidelines want to be strictly related to the teleoperation system that we want to use, while this issue, in my opinion, is more related on how you decide to collect the data, and I will explain a bit better. So there is a paper now, I don't remember which one it is, but where they say tried to they asked the users that were teleoperating the robot to try to explore as much as possible the workspace of the robot, like opening a drawer, taking the things that were inside, changing the places of things, and by this they were able to let's say avoid these redundancies that might of course occur, but this is more related to what you ask the user to do, not how you design the teleoperation system. Okay. So that's why we didn't include that.
Okay. Thanks. Any other questions? Okay, if not, thank you so much, Alberto, for the talk.